Now, to understand grouping, we should proceed in the following way. Why are we working with a random effects model at all, or a mixed effects model at all? Because out of the two inputs, one of them is random, namely the tablet input. The particular tablets that we have used in our experiment are of no particular concern. That is why we are going into mixed effects model. So R starts by identifying that input, in this case that is tablet, that is our subscript J. Wherever that subscript will occur, the corresponding coefficient will become random. Here we have only one such. It calls that thing as group. For example, here is group 1. We have got 10 groups. Wherever B1 coefficient occurs, that is one group. So both these things come from tablet 1. Similarly, here is another group. I have got 1, 2, 3, 4, 5. So this is for tablet 5. These blue rows correspond to tablet 5. So instead of saying I have got 20 rows, R likes to think of it as 10 pairs of numbers, which is of course the natural way to think about it. Each tablet is called a group, and this is an example of a grouped data. This terminology is by no means standard. It is just used by R. So we have a group data. Now what R suggests is that you look at each group separately. Let's look at the red group first. You will notice that in the fixed part you have got 1, 1, then a 0. Here again 1, 0, 1. Look at the blue part now. Again you have 1, 1, 0 and 1, 0, 1. In this way, whichever tablet you take, if you restrict your attention to only the corresponding two rows, you will find that you are having the exact same submatrix in all the cases, and that is natural because that is the fixed effects part, that it does not involve the subscript J. So if you group by subscript J, you will not see any effect here. If you change just J, the parts free of J will not change. Now if you look at the part which is the random effects part, you will see that in the red part only B1 plays any role. So for the red part, B2 to B10, they are just absent. So if I focus my attention on only one random effect, namely B1, then the matrix is simply 1, 1. So if I restrict my attention to any single group, the fixed part is just 1, 1, 0, 1, 0, 1, and the random effect part is again the same 1, 1. This 1, 1 keeps on shifting place, but for every group I have got only one particular random effect coefficient to consider. With respect to that random effect coefficient, it is always 1, 1. This is bound to be the case in every situation, because had this not been the case, that means you are associating separate importance to the different tablets, and that is something that we are not doing. So the model is always bound to look like this. Focus your attention on only the jth group. In that case, that subvector yj will have the corresponding model. It will have some x times beta, which I have called x tilde, not same as the original x. This was my original x. My x tilde is only this little small thing. Then you will have only bj, not the entire b vector, only bj. And it will be multiplied by something which is again free of j, which I have called z tilde. In our case, it is simply 1, 1. And then the corresponding error vector, restricted to only the case where we have the subscript j. So we are always bound to have this thing. So the big X and the big Z must have this special structure. It is made by repeating the small x tilde again and again and small z tilde again and again. The x thing is just repeated one below other. The z things are repeated in a diagonal fashion. R suggests that you model these two things. When you are specifying the design matrix, you specify these two small things and not the big thing. Now, this might look weird. It is weird, but I think the main advantage of thinking in this way is that you can avoid writing nonsensical models. You can write, for example, if you just use the general notation, a polynomial regression where the linear term and the cubic terms are fixed, but the quadratic term is random. It is possible to write it, but obviously it is not of any practical use. The way R forces you to write is by identifying the cause behind the genesis of the random effect and then follow along that line. Whenever that particular J is present, you make it random. So you are always writing a model which is meaningful. It is possible to write meaningless model even in this case, but kind of more difficult to do so. I do not know whether the creators of the package really thought along this line, but that is one way of justifying it.